Hi, welcome. This is measure theory session number 11, and we had already completed all the basic results about Lebesgue measurable sets. Today we are going to talk about existence of non-measurable sets. That means the class of measurable sets is a proper subclass of the class of all subsets. That is, script M is strictly contained in the power set of R. Okay. And those who had watched my first two or three videos where I gave motivation, I already said that. Okay. In fact, perhaps I am the only one. My book is going to be perhaps the only one which talks about non-measurable sets even before we talk about measure theory. Okay. Why it is needed. Anyway, let's get started. And if time permits, after that, I will give quick summary of what we have done so far. Okay, and I have a piece of advice at the end. So, what we plan to do is the following. This is the class of measurable sets. And we are going to say it's properly contained in P of R. That is power set of R or power set of R. What does that mean? That means there exists a subset E of R such that E is not measurable. Okay, we will go through the proof. Then we will also try to understand what the proof tries to say. Let me see whether I started the recording. Yeah, good. Nowadays I'm becoming, okay, I have to be becoming paranoid in some sense. Okay, right? The way we do that is very interesting. So let us look at E, not, okay, this is not the E if you want. Look at J or I. Okay, I equal to the usual unit interval, right? Then I want to define an equivalence relation. I say x and y, x is related to y, if and only if x minus y is rational. Okay, it is very easy to check. This is an equivalence relation. You are all MSc students, so I don't want to spend time on such thing. Okay, this is an equivalence relation. Okay, then, so, and as usual, this denotes the equivalence class. Class of x, where x is in 0, 1. Okay. Therefore, my I is written as union of equivalence classes, right? And we will assume this is a pairwise. This is pairwise disjoint. Okay. I'm not writing x in thing 0, 1 because, okay, if x and let us say something like x plus a rational, that's that. If this also belong to that, okay, this is my y, then x and y, they will be equal, right? So I should not write x in 0, 1. This is wrong. You should simply say union of equivalence classes. Now we want to invoke what is called axiom of choice. Many of you, due to algebra, either in linear algebra, the existence of a basis for a general vector space or any field, or existence of maximal ideal, etc., you would have made use of Zorn's lemma, partial order, maximal element, all such things. But axiom of choice, perhaps not much used. Okay, this is the first time. The second instance is when you want to define Cartesian product of arbitrary collection family of sets. Anyway, so let me quickly state what is axiom of choice, then we shall use it. So axiom of choice says, suppose AI is an index family, is a collection family of subsets, indexed family of sets, okay, indexed by I. Okay, what it says is, okay, there exists for each I, okay, there is an xi in I. Okay, I can choose one element. This looks very obvious, okay, but as believe me, this there is a bone of contention about this, especially logicians look down upon this in some sense, okay, they are wary of this. Let's not worry about it. Let's go through what it means. That is, there is a choice function f, let me call it f, is called a choice function. There exists a choice function from I to union ai such that f at I belong to ai. That fi is what we call xi. Okay, if you remember Cartesian product, okay, this simply means the Cartesian product of a is not empty. Okay, but for our understanding, let me just quickly say what it means is, from each ai, well, I can choose one element xi in ai for each I. That's all it means. Okay, is that clear to you? Right. And since f is a function, this xi has to be unique because f at I is unique, right? We call it xi. That means for each I in I can choose a unique xi in ai. Okay, it may happen a equal to aj, but doesn't matter. As far as my xi, that from that I choose xi. That is why it's easier to use choice function. Okay, please pause, review, proceed. So there is a choice function from I to union ai such that f at I belong to a. Okay, that this f at I is what I call xi. That is in a. Okay, this. Now let's go back. So on 0 1 I wrote it, okay, let x be the set of equivalence classes, okay, this is a, so what do I want to do is, by axiom of choice, okay, there exists a set E such that E intersection script x is a singleton. Again, try to understand, don't be intimidated. Okay, I'm not now writing in terms of indexing set. The indexing set I want is to be again equivalence classes only. Okay, please do not bother about this, try to understand this. So what we mean is, this is the important thing. By axiom of choice, I can, okay, there exists a subset E in R with what property, so that for all x in 0 1, the equivalence class of it has exactly one element from this. That is, E meets any equivalence class exactly at one point. Okay, please make sure you understand these things properly, because axiom of choice is, okay, now we're taught, and so this is the first time we are using possibly, so please understand. Okay, let me just make sure again. I am in screen sharing mode. Yes. Okay, now what, notice that E is a subset of 0. That's clear, right? We want to show, okay, E is not measurable. Okay, right? Now how do we prove that? Let us make a series of observation. Okay, Suppose x and y are in 0, 1, okay, and x is equivalent to y, that means x minus y is rational number, right? Now I want to get a bound for this, okay? This rational number, call it R, where does it belong to? Okay, notice that x minus y, since I can put an upper bound, since x belong to 0, 1, x is less than or equal to 1, since y belong to this 0, 1, y is greater than or equal to 0, therefore minus y is less than or equal to 0, therefore 1 minus y, that's the less than or equal to 1. Yeah, do you understand that? Yeah, therefore this rational number R should be less than or equal to 1. For a similar reason, okay, x belong to this, therefore x is greater than or equal to 0, and y belong to 0, therefore y is less than or equal to 1, therefore minus y is greater than or equal to minus 1, therefore this one, therefore minus 1. Therefore, okay, for any x and y in R 0, 1, okay, x minus y lies in minus 1 to plus 1. It's a rational number and it lies in this, okay, if x is equal to y. Is that clear? So pause. We proved x minus y lies between minus 1 to plus 1, but we also proved as a rational number, if x and y are equivalent, x minus y is rational, therefore it has to be, it lies in the set of rationals in the interval minus 1 to plus 1. That's all you have proved. Okay. Second thing, so now we know that minus 1 to plus 1 intersection q is countable. Okay. So let Rn be equal to this set, countable set. Okay. So this be, yeah, all the rationals in this interval 0, 1. This is called an enumeration. Okay, let Rn be an enumeration of these things. Is that clear? Okay. So what you said is Rn lies in the interval minus 1 to plus 1 for all n. Okay. Next. Again, let us see as if I take Rn plus E, where E is this set. What is the E? E is the set which has exactly one element from each of the equivalence class. Okay. So I want to know where it is contained in. And does it contain anything? No, not does it contain. Let me see. One. Right? Okay. Now where does it belong to? Notice that my E is a subset of 0, 1. Therefore, any element is of the form Rn plus x, x is in E. And x is in 0. And my Rn lies between minus 1 and plus 1. Therefore, this fellow will lie between Rn plus x, will lie x. This is less than or equal to 1 and less than or equal to 1, x is less than or equal to 1. Whereas Rn is greater than or equal to minus 1, x is greater than or equal to 0. Therefore, it is equal to minus 1. That means, okay, Rn plus E is contained in minus 1 to 2. This is true for all n. Make sure that you follow this. Right? And hence the union Rn plus E over n is contained in minus 1 to 2. Okay? Right. Now the third thing is I want to claim, this is the third observation, if n is not equal to m, then Rm plus E and Rn plus E, they are disjoint. That means this collection Rn plus E as n varies over n is pairwise disjoint family. This is a countable family. Why? Suppose x belongs to this, right? That means x is of the form, let me say z. Z is of the form Rm plus x where x belong to E, that's also equal to Rn plus y where y belong to E, right? And hence you can see that Rn minus Rm minus Rn equal to y minus x, or other way around. Yeah, Rm minus Rn equal to y minus x. That means y, these are all rational numbers, therefore y is equivalent to x. Okay, but remember, where are they? Y and x are in E, and y and x, they belong to the same equivalence class, but E has only one unique element from each of the equivalence class. Therefore, we conclude x equal to y. Make sure you understand this. Therefore, my z is Rm plus x equal to Rn plus x. This implies Rm equal to Rn. Okay, this is a contradiction. So, therefore, we conclude Rm plus intersection Rn plus E is empty if M is not equal to N. Right? So, look at in summary, what have we done? Okay, on 0, 1, we introduced an equivalence relation if x minus y belong to Q. Then E is this a set which has exactly one element from each of the equivalence classes. Right? Why is such an E exists? Why does it exist? Because of axiom of choice. Right? Then what did we observe about this? We observed that, okay, if x and y are in 0, 1, then x minus y, okay, lies between 1 and minus 1. Therefore, we saw that if x and y are in E, x is equal, in 0, 1, and x is equivalent to y, then x minus y is a rational number. It belongs to minus 1 to plus 1 intersect with Q. And let Rn be the enumeration of all these rationals in here. Then we proved that Rn plus E is contained in minus 1 to 2. And also we proved that Rn plus E is a pairwise disjoint collection. Okay. These are the facts we need now. Now, what we wanted to claim is E is not measurable. Okay, this is the claim. Suppose not. Therefore, E is measurable. Right? If E is measurable, then E plus Rn is measurable for all n. Right? We proved translation of measurable set is measurable. Right? Okay. And this is a countable family. Therefore, next thing we know is M of E plus Rn is same as M of E for all n. Okay. Right? Now this collection maybe Rn plus E. Pardon me if I am writing it differently. Rn plus E as n varies. This is a pairwise disjoint measurable sets. It's a countable family. Therefore, what I know is the union Rn plus E is measurable. And measure of this union, because this is a disjoint collection, this is going to be measure of each of the thing. But this is going to be M of E from n equal to 1 to infinity. Each term is a constant term M of E. Is that clear? Right. Now union Rn plus E if we know it's already contained in 1 to 2. Therefore, by monotonicity, measure of the union Rn plus E must be less than or equal to minus 3. Sorry, less than or equal to plus 3. Right? Okay. Therefore, this fellow, what we have is, this will be at most 3. Okay. Therefore, since measure of union Rn plus E equal to summation measure of E 1 to infinity, this should be less than or equal to 3. Right? Now, what is the possibility for the measure? Either this is 0 or this is positive. These are the two possibilities, right? Now, if this is 0, then what is this infinite series? The sum of the infinite series. Okay, all the partial sums are 0, therefore the sum is 0. Because the partial sums are 1 to n, m of e plus m of e n times. This is a partial sum, that is 0, right? Therefore, the limit of the partial sums is 0, therefore the measure is 0. Yeah, correct. Is that clear? Okay. But that's a contradiction, because remember, union Rn plus E, we wanted to say it contains 0, 1. Maybe did I say that? No, sorry, I forgot to say that. That's okay. Let me give the. So a fourth property we need is the unit interval 0, 1 is contained in Rn plus E. Okay. Why is that? Start with any y in 0, 1, then there is a unique equivalence class x which is in E, right? Therefore, this y belong to x, that is same y minus x is a rational number Rn for some n. That means y belong to Rn plus E, right? Is that clear to you? Yeah. So what you would actually observe is this. Okay, this is contained in union Rn plus E, and this is contained in minus 1 to 2. Therefore, by again monotonicity, measure of 0, 1 should be less than or equal to measure of the union Rn plus E, but that is equal to summation measure of E 1 to infinity, and that should be less than or equal to measure of minus 1 to 2, that is length, which is 3, and this is 1, right? Therefore, what I know is measure of E infinitely many times, this should be less than or equal to 3 and less than or equal to 1, right? Now, there are two cases. M of E is 0. If M of E is 0, the partial sums are 0. Of this sequence is 0. Hence, summation M of E is 0. But then we get 1 is less than or equal to 0, a contradiction or absurdity. Or second case, M of E, let us say, is alpha, which is positive. Okay. Then the partial sums are n times alpha. Okay. By Archimedean property, there exists n such that n times alpha is strictly greater than 3, and hence summation, okay, m of alpha is greater than 3 at least, right? But it has to be less than or equal to 3. That's again a contradiction. So therefore, if E, the whole thing was, we assume E is measurable. Since it's measurable, either m of E is 0 or m of E is positive. Okay, and whatever be the condition, we arrived at a contradiction. Therefore, the only conclusion is E is not measurable. So pause, review, proceed. Please review the proof, pause, review, and you will see the actually it's simple. Do not get frightened. Okay. And many interviews they ask as though it's a very difficult thing, but it's actually very, very easy construction, except it's ingenious construction due to Italy. Okay. But it's very easy. Please go through that. Okay. Now we will try to see what went through the proof. Huh? Where did we use the fact it's a Lebesgue measure or anything? Yeah, let us see that. If you go through the proof, what we needed to assume that was m of and intervals are measurable and their length of j and countable additivity, and notice that this implies monotonicity and finite additivity. Okay, and translation invariance of the measure. All right. So with these three things, okay. So if I have any a function p, okay, from p of r to 0 infinity, which has all these three properties, that is mu of j is length of j, and mu of a plus j is a plus e is mu of e, and mu is countable additive. Okay, then there will always be non-measurable set. Okay, this is what we saw in the first three lectures of motivation and geometric ideas. Okay, this is just a summary, but don't worry if you don't follow. Go through the earlier ones. Okay, first understand what did axiom of choice said, and axiom of choice, from that what we conclude was the existence of a set E with what property? E has exactly one element. It has one element from each equivalence class and only one element. Okay, both are important. It has at least one element and it has at most one element. Okay, both are. That fact we used. Okay, please go through that. That's it. Now next thing what I said is I want to quickly summarize what went through the lecture so far. Okay, because you will be surprised if at all you want to use measure theory, Lebesgue integration later in your life. If you become an analyst of any kind, okay, like a PDE guy, harmonic analysis, or Euclidean analysis, or analysis on manifolds, anywhere, the only facts you will need about Lebesgue measure theory are going to be the following. You don't have to worry about how you constructed outer measure. I mean, how do you construct a Lebesgue measure and how do you prove all those things? What all you need is the following facts. Okay, I'll try to show. Maybe in fact, it is summarized in our functional analysis book by Sukumar and myself. Okay, it's essentially the same thing I'm reproducing in here. In a forthcoming measure theory book also, I have written the same thing. In functional analysis, I call it executive summary. Here I call it a summary. That's the only difference. Okay, let us try to see that. Let me screen share. Okay, I hope all of you are able to see. Okay, I will just read it. There is nothing more to say. Okay, we find the beginners in the subject are lost with too much details involved in the construction of the Lebesgue measure, because you have to talk about outer measure, what's the definition, how you got it. Okay, then establish various properties. Okay, and then we have to define what is meant by Lebesgue measurable sets, then establish the properties, right? But if you continue to do analysis, you may realize later that you do not need the details of the construction. The only facts which are needed are summarized here. What are they? there exists a class M of subsets of Rn called Lebesgue measurable sets and a real valued extended real valued function M to 0 infinity, infinity included. What are the properties? The first thing is M contains all the intervals. Okay, it contains open sets, it contains closed sets, and it contains G data sets, it contains F sigma set. I have not defined what is Borel sigma algebra, let us not worry about it at present. Then the second thing is empty set belong to this, because I said intervals belong to that, open set belong to that, therefore empty set naturally belong to that, R or R and also belong to that. The important thing is whenever A belong to that, its complement also is measurable. The second thing we did that was whenever I have a collection, countable collection of measurable sets, their union and the intersections are measurable. Okay. And then the measure M has the important property, namely if J is an interval, measure of J is equal to length of the interval. Okay. And the third thing, the next thing is it is translation invariant, and sometime I may need the fact how I define the measure. That is the definition. Remember, measure is nothing other than outer measure restricted to the class of measurable sets. Therefore, this is the outer measure definition. Okay. And this is the seventh property, is the basic one. Okay. Whenever you give a countable collection of pairwise disjoint measurable sets, then measure of the union equal to sum of the measures. Okay. In particular, finite additivity follows because I can take, okay, A equal to A1, B equal to A2, A3 onwards empty set, then you will see the union AN is going to be A union B, that is going to be M of A1 plus M of A2 plus 0, 0, 0. That is M of A plus M of B. Okay. And in particular, if A is contained in B, measure of A is contained in measure of B. That is monotonicity. Finite additivity, monotonicity follows. And another important property is if I have any non-empty open set, its outer measure is positive always. Because if I have X in U, there is an interval J which is contained in that open interval. And the length of the open interval, it's a non-empty open interval because X belongs to that. Therefore, it's a positive. By monotonicity, M of U must be positive. Yeah? Do you want me to write? I hope I will not confuse any problem. See, if U is open, okay, there is a G, X in, therefore there is X minus epsilon to X plus epsilon. An interval J which is contained in U. The monotonicity M of U is greater than or equal to M of J, but that is 2 epsilon. Therefore, it's positive. That's all we mean. Yeah. The next thing is what we looked at, regularity. What did the regularity say? Regularity said that whenever if E is any measurable set, okay, and epsilon is given, there is a G open, so that E is contained in G and measure of G minus E is less than epsilon. That means I can approximate E from the above by means of open set. Similarly, there is a closed set, so that F is contained in E now and measure of E minus F is less than epsilon. That means I can approximate E from inside by means of a closed set. And the next thing is if M of E is finite, then for every epsilon positive there is a compact set. Okay. I can approximate any set of finite measure from below, from inside by means of compact sets. Okay. So what does that mean? Notice that the first one says that M of E therefore is nothing other than GLB of M of U, where U is open and E is contained in U. That is equal to LUB of M of F, where F is closed and F is contained in E. And in the case of finite thing, I can take M of K, where K is compact, K is contained in E. Okay, these are the things. So another important property of Lebesgue measure is if E is a measure 0 and F is a subset of E, then F is also measurable and measure of F of course is 0. Look, okay, this is called completeness. That is, the Lebesgue measure M is complete. This is just a technical term. Okay, we will again define it later. What does it mean? It says that whenever I have a set E whose measure is 0, and if I know A is a subset of E, then A also should be measurable. That's a more important thing. Okay, automatically M of A will be 0. That is easy because of monotonicity. So the crucial thing is this. This is a very crucial thing. Okay, this is what is called completeness. Okay, let me just check whether I have said everything. Okay. So later, when you want to use anything to the Lebesgue measurable sets in future, forget about your exams that you want to go through. Okay, you will only need these facts. You will not worry about how you got the proof or anything. Okay, and later the only way you will use will be measurable functions and integrals of measurable functions and the various convergence theorems will come. Don't worry about that. Oh, they are the very powerful tools. This construction is some kind of a building. All the bricks are needed. We got the building. After that, we have to live in. That living in process is going to be measurable functions and integrability of such functions. That's what next few lectures we will talk about measurable functions. Okay. I hope you enjoyed the lecture. We will meet again. Stay safe.